There we go. Okay. So after class, I hung around and kind of communicated with Canvas. Communicated with Canvas, and it seems like they figured out what was wrong with the Canvas recording, and some people were having trouble viewing it. So hopefully they took care of it, or I spent 2 hours going back and forth with them for nothing. So hopefully it's all fixed. All right, so today we're going to start section 6.3 and probably finish 6.3 and start 6.4, because 6.4 covers quite a bit. So we should finish 6.3 and 6.4 between today and tomorrow. But 6.3 covers the shell method. Okay, and just like with most of our methods, we're going to kind of visualize on our X and Y axis. What if we have just any random function? And we'll just kind of draw any random function there. And on that, we're just going to look at the interval from A to B. And this is our function y is equal to f of x. Okay, so in that interval, we're just going to draw little random rectangles. And the rectangles can be anywhere, at least for now. Okay. So we know that the width of each rectangle is just from x of I minus 1 to x of I. Okay, so that could be x1 to x2, x2 to x3, x3 to x4. Just kind of put it into a general form. Okay. With the shell method, what we do is we measure the width of each of those rectangles and we kind of spin it around the y-axis. Measure the width of the rectangle and rotate around the y-axis. Okay. Let's say if we get this first rectangle and we just kind of spin it around the y-axis. Okay. Not the whole thing, just that one rectangle. So if we spin it around, Because A is not on the y-axis, you'll have that little hole in the middle. But if you spin it around the y-axis, kind of look like that. Of course, not as crooked, but straight. There we go. Try to straighten it out a little bit. Okay. So the width of that is just our x of I minus 1 x of I, because we just got that and spun it around. Okay, so the width of that still, the inside of that would be your x of I minus 1. This outside edge would be your x of I. So from here, all we're going to do is piggyback on the fact that we know that the volume is equal to the circumference times the height. Didn't have enough room. I knew that when I first started writing. Volume equals circumference times the height times the width. Make that H a little bit neater. There we go. Now, one thing we definitely know is that if we use the rectangle Riemann sum, rectangle Riemann sum, we know that your rectangle will have the intersection at some value C, where part of the rectangle is over the function and part of it is under the function, which means that value C will be very, very close to the approximate area of that rectangle. Because if you're a little bit over and you're a little bit under, then at some point, one of those points has to be exact. If it's not exact, then it's really, 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 really close. Okay. So that means if there's an midpoint, that exists. And we'll call that x of I with a little bar over it. Sometimes you see a bar, sometimes you see like a little hat. It varies. Depends on the textbook. That means that there will be an x of I with a little bar in between your x of I minus 1 and x of I. So it's an element of your x of I minus 1, x of I. Okay, that little symbol just means an element of. Yep, an element of that, or just basically one of the in between that interval, somewhere in that interval. Okay. So if we were lucky enough to be able to find that midpoint, then we know that this would be our exact volume. We don't have to worry about having a lower volume or upper volume. It's right at the correct midpoint. This would be our exact volume. Okay. So if we did this for, let's say, the first rectangle under the function. Okay, we ended up with our circle there. So we're not going to draw the sides, but let's say we did it for the next rectangle, which was right next to it. And that would revolve around there. And then the third one, and the fourth one, and the fifth one, and the sixth one, and it kept on going and going and going. Okay, so all of those rectangles will go from x of I to x of I minus 1. Each one of those, top of those, will just go from x of I to x of I minus 1. x1 to x2, x2 to x3, x3 to x4, et cetera, and so on. So it should kind of look like a shell. So again, the number of rectangles, we want to get them as many as we possibly can, because the more rectangles we have up here, the more accurate our actual volume will be. So we're going to have the sum from I equals 1 to n of 2 pi times x of I of our midpoint. Okay, so that actually gives us our circumference. times f of x sub I, which gives us the height. That's our f of x at any particular point. And the width, that's your x sub I to x sub I minus 1, which is your delta x, which is denoted as delta x, which is your width. So that would give us the volume of that particular shape, but because if we have a set number, then our approximation would be, it could be close, but it wouldn't be very accurate. So we have to increase the number of rotations, which means that our volume, to be as accurate as possible, would have to be the limit as the number of rotations approach infinity. So the more rectangles, the more accurate. Of 2 pi times x sub x bar sub I. Oh, forgot to put my bar up here. Should be f of x bar. So I delta x. If we look at this, this is just the limit definition of an integral. So our volume is just equal to the integral from a to b, 2 pi x f of x with respect to x. Yes.
For the integral version of it,
Mhm.
do those ones not have the bar and sub I?
Which part of it?
The last part that you circled, like the 2 pi x.
Oh, yep. We only need the bar because we're just looking at a certain point in the rectangle. But if we make those rectangles small enough, then it kind of blends into the whole thing. So picking that one point, if that rectangle really shrinks, then the whole rectangle is about the width of that one point. So that's why the bar can kind of disappear from there. You're welcome. All right. Anyone still writing? Okay. So let's say, for example, that R is the region bounded above by the graph of f of x equals 4x minus 2x squared, and bounded below by the x-axis over the interval from x equals 0 to x equals 1. Okay, so we want to use the shell method. To find the volume of the solid of revolution by revolving our region around the y-axis. Now with this one, because they told you that you're going to use the shell method, you don't really need the graph, but I'll graph it just to show you exactly what we're going to be doing. Okay, so if we look at the graph of 4x minus 2x squared, it kind of looks like this. We know y is equal to 2 and x is equal to 1. Now we're just looking for the interval from 0 to 1. So we're just looking for this part of it because it's bounded below by the x-axis. So we're going to get this part of it, and we're going to revolve that around the y-axis. So I'm not going to even attempt to draw what it would look like because I know I would mess it up and probably confuse you more than anything else, but kind of use your imagination to imagine if this part just revolved around the y-axis. Yeah, that looks like a 4. Let me make that look more like a y. Go. So we know that the volume, the integral from a to b, 2 pi x times f of x with respect to x. So that 2 pi, we can go ahead and just factor that out to the front. We know that our upper and lower bound will be 0 and 1. So that's the integral from 0 to 1. We have that 2 pi that we factored out. And your f of x is just x times 4x minus 2x squared. With respect to x. So go ahead and distribute that x. You know, our volume is equal to 2 pi times the integral from 0 to 1 of 4x squared minus 2x to the third. With respect to x. Now from there, we can just go ahead and integrate each term. So we know that the volume will equal 2 pi times 4 times the integral of 4x squared, which is 4 times x to the third power over 3. Let me clean that up a little. There we go. Minus 2 times the integral of x to the third power, which is x to the fourth power over 4. And that's from x equals 0 to 1. So if we go ahead and apply the fundamental theorem, our volume would equal 2 pi times, we go ahead and plug in our upper bound. So that gives us 4 over 3 times 1 to the third power. Minus 2/4, so we can just go ahead and make that 1/2 times x to the fourth power. So that's 1 to the fourth power. Make a little room for my closing parenthesis. Here we go. Minus, and we know this is going to be 0, but I'll write it out anyway. 4 over 3 times 0 to the third power minus 2 over 4, which you could just make 1/2 of 0 to the fourth power. And again, that just becomes 0, so those disappear. So we know that our volume is equal to 2 pi times 4 over 3 times 1 is just 4/3 minus 1/2. Where if they want a decimal approximation, you can just plug it into your calculator, but if they want the exact value, we can do that too. We can rewrite 4 over 3 as 8 divided by 6, and 1/2 as 3 divided by 6. We have 2 pi times 5 over 6. Well, we can simplify that. 2 goes into 2 once, and it goes to 6 3 times. So that leaves us with a volume of 5 pi over 3. All right. Any questions on that one? All right. Anyone still writing? Okay. So let's say, for example, if we know we have a region R, so R is the region bounded above by the graph of f of x is equal to x to the 3/4 power. And below by the x-axis. Over the interval from x equals 0 to x equals 6. Excuse me. Okay. We want to find the volume of the solid. Solid of revolution by revolving, solid of revolution by revolving our region around the y-axis. So again, you don't have to graph it, but a lot of times it does help to know what you're solving for. Okay, so f of x equals x to the 3/4 power kind of resembles the square root of x function. X to the 3/4 power. Okay, but we're just looking for the interval from x equals 0 to 6. So we'll say 6 is somewhere around here. So we're just looking for this interval right here. So if we revolve this around the y-axis, kind of have this little opening here. And the other half kind of looks like a mirror image. So it would look sort of like that. Let me get my little circle here and make that a little clearer. Oh, that didn't help. There you go. That's a little bit better. Okay, so we know that our volume would equal to the integral from a to b. And again, that 2 pi, we can factor that out right from the beginning. Oops. Times the integral from a to b of x times f of x with respect to x. Okay, so that gives us the volume is equal to 2 pi times the integral from 0 to 6 of x times x to the 3/4 power with respect to x. Well, we can go ahead and combine these two. We're just multiplying x and x to the 3/4 power. And we know that x to the power of a times x to the power of b is just x to the power of a plus b. So that means we have x, or x to the first power, times x to the 3/4 power. That's just x to the power of 1 plus 3/4. So if we change that 1 to 4/4, we get x to the 4/4 plus 3/4. So we have x to the 7/4 power. So that means our volume would equal 2 pi times the integral from 0 to 6 of x to the 7/4 power with respect to x. Okay, so we can go ahead and just integrate this. So it's 2 pi times the integral of x to the 7/4 power is x to the 7/4 power plus 1 divided by 7/4 plus 1. So that'll be x to the 11/4 power divided by 11/4. And I'll leave a little bit of space after that because we want to get rid of that 11/4. And that's from 0 to 6. Okay, so we want to get rid of that 11/4 in the denominator because it's just too doggone distracting. So we're going to multiply the numerator and denominator by the reciprocal. So we're going to flip that and multiply it by 4/11. and 4 over 11. Okay. So if we multiply the two denominator values or factors, we get 44 over 44, which is 1. So those two cancel each other out and give us 1. And the 1 in the numerator, we can just move that one right over here. Just factor it right out to the front. So our volume will equal 2 pi times 4 over 11 times x to the 11th fourth power. There we go. X equals 0 to 6. Okay. Then from there, we just go ahead and apply the fundamental theorem. So it's going to equal, we can go ahead and combine those two and give us 8 over 11 pi. Or 8 pi over 11, whichever way you'd like to write it. So if we plug in our upper bound, that would give us 6 to the 11 fourth power minus, plug in our lower bound, 0 to the 11 fourth power, which is just 0. So we really didn't have to write that one. So that gives us a volume, which is equal to 8 pi over 11 times 6 and 11 fourths power, which isn't the simplified version of that answer. So 9 times out of 10, if they want it in the simplest form, simplest exact form, then you'd have to kind of simplify that a little bit more. Okay, and we can do that right here on the side. If we have 6 to the 11 fourths power. Here we go. Well, since we have a denominator of 4, we could rewrite that as 6 to the 4 over 4 power plus 4 over 4 plus 3 over 4. Or you could just divide it by 4, 11 divided by 4. See, it goes in there twice. Okay, so that just gives us 6 to the power of 1 plus 1 plus 3/4. So we add those two together, you have 6 squared, jumping ahead, plus 3/4. It gives us 6 squared times 6 to the 3/4 power. And again, you could have got the same answer if you just divided 11 by 4. So this is kind of my long way around. That would have still given you 2 3/4. Okay, so now we can get that. We have 8 pi over 11 times 6 squared times 6 3/4. Move that out the way. now we can actually go ahead and multiply 6 squared by 8. So that gives us 288 pi over 11 times 6 3/4. Or 6 to the 3/4 power, not 6 3/4. Okay. So again, they might take it in this form. I'm not saying they won't, but Newton, from one semester to the next, they could be really strict and they get a little lenient, or they could be lenient and get really strict. It varies. So always kind of have a backup plan when putting your answer in when dealing with Newton. Oops. All right. Any questions on that one? Yes.
Would we also just be able to just plug it all into a calculator and put that answer into the unit?
If your calculator gave you that answer, then you'd be perfectly okay with that. So it depends on the type of calculator you're using. So now, if they said just put in a decimal approximation, yeah, I would have plugged into the calculator right from the very beginning, just to make it easier. So honestly, a lot of these I just show all the work because that's just kind of how my head is wired. But a lot of those, if you plug the graph into the calculator, you could avoid a lot of steps. Like if you had we want to find the function above and below, you can just plug both of them in the calculator and it'll show you. You won't have to go through all that work. So, if you don't have a graphing calculator, it's pretty decent investment for this class. I don't know if you're still going to use it later on, but for this class, it definitely helps. I wouldn't go out and get the biggest and grandest of them all, but if you can borrow one from someone who they're not using it, that's definitely helpful. All right, anyone still writing? All right. Ooh. So let's say, for example, R is the region bounded above by the graph of f of x is equal to sine of 4x squared, and below by the x-axis. Over the interval from x equals 0 to x equals the square root of 3 pi over 2. Find the volume of the solid of revolution formed by revolving our region about the y-axis. we know that our volume is equal to 2 pi times the integral from a to b of x, f of x, with respect to x. So that means our volume will equal 2 pi times the integral from 0. Should have given that a little more room. I want to write that big enough to where you can actually read it. Move that down some. Pi from 0 to the square root of 3 pi over 2. 3 pi over 2. Of x times f of x, so x times sine of 4x squared, with respect to x. So we can find the integral of sine of 4x squared times x, but to do that, we have to use our u substitution. Sine of 4x squared times x with respect to x. Okay. So for this one, we're going to let u equal 4x squared. So the derivative of u in differential form, using the power rule, we bring down the 2, so that's 8x with respect to x. So if we divide both sides by 8, we have du divided by 8 is equal to x dx. Okay, so I'm just going to switch these around. You don't have to. I just like to do them when I'm explaining it. So instead of x times sine, we have sine of 4x squared times x. Makes it not mandatory, just helps with the explanation. Clean up that parenthesis a little bit. Okay, so we can rewrite this as our volume is equal to 2 pi times the integral from 0 to the square root 3 pi over 2. Since our u is equal to 4x squared, we just replace that and make it sine of u. And our x dx, well, we know that's equal to du over 8. So if we change that to du times 1 over 8 and just factor that 1 over 8 out to the front, our volume is equal to 2 pi times 1 over 8 times the integral from 0 to the square root of 3 pi over 2. of sine of u with respect to u. Well, we know that the integral of sine of x or sine of u doesn't matter. It's just negative cosine. Well, plus c, but we have a definite integral, so we don't have to worry about the plus c. So if we simplify, but combine those two, 2 pi times 1 over 8 is just 2 pi over 8 or pi over 4. And we know that the integral of sine of u with respect to u is just negative cosine of u. And I'll use the bracket since we're going to put the upper and lower bounds in there. There we go. Okay. But we know that this is from x equals 0 to x equals square root of 3 pi over 2. So you could do one of two things. You could say, okay, we're going to find u of 0 and u of square root of 3 pi over 2. Or we could just convert that u back to a function of x and plug it in. And normally that's what I do. I just go ahead and replace the u. This way I don't have to change both of those. So we can factor out that -1 also. Where our volume is equal to negative pi over 4. And instead of cosine of u, we can just replace the u with 4x squared. Cosine of 4x squared from 0 to the square root of 3 pi over 2. Oops, there we go. So now that we have all of that taken care of, we can finally use our fundamental theorem now that we have the independent variables matching up like they should. Okay, so volume is equal to negative pi over 4. So we're going to plug in our upper bound. That's cosine of 4 times the square root of 3 pi over 2 squared. Now we plug in our lower bound, so it's minus cosine of 4 times 0 squared, which we could have just put 0, but I like to write out the whole thing. We know 4 times 0 is just 0, so that just disappears. So our volume is negative pi over 4 times cosine of 4, and you have the square root of 3 pi over 2 squared. So we know that square and that square root will cancel each other out. So that's just 3 pi over 2. Minus cosine of 0. All right, so simplifying it a little bit more, we have negative pi over 4. And we have cosine of 4 times 3 pi, so we have 12 pi divided by 2, which is 6 pi. Minus cosine of 0, if you want, you can just replace that with 1, instead of writing cosine of 0 over again. Okay, so we know cosine of 6 pi, negative pi over 4, and cosine of 6 pi is actually 1. So 1 minus 1. So you have negative pi over 4 times 0, which is just 0. And I used to hate problems like this when I was a student. Go through all that work to end up with 0. I got to guess 0, but yeah, that used to burn me up. Like, I'm going to go through all that work, at least let me see a decent number. All right, any questions on that one? All right, anyone still writing? Okay. Cool. All right. So we're going to go ahead and start on section 6.4. And that starts off with the arc length. Oops. And that's going to kind of expand on what we already know is the distance formula. So this formula for the arc length just piggybacks off that one. Okay, so what if we have a curved function, and make that a little longer. and some random curve function. And we're just looking for some interval from A to B. Okay, so we're going to say our x of 0 is our A. If we go all the way to the end of our subintervals, our x of n would equal B. Okay, so let's say if we start right here at our x of 1, x of 0. Actually, we can call this x of 1 just to keep it in line with the actual distance formula. No need in changing notation. Okay. So if you have any curved object, if you zoom in close enough, I don't care how much of a curve a circle has, if you zoom in close enough, the distance between any 2 points on that curve will look like a straight line. And a circle, you could just draw that as a series of very, very small straight lines. So it just keeps on going a straight line, straight line, straight line. If they're small enough, once you zoom back out, you'll never be able to tell. So that's what we're going to do here. We're going to zoom in so close to this point here. We'll call that just above our x of 2. To where we're going to take that, and let's say it's almost infinitely close together, and we're going to magnify it. So we're going to get that portion of it. And we're going to call that our length s of 2. Oh, not s of 2, s of 1. Jumping ahead when I thought the x of 2. So length s of 1. Okay. Well, if we zoomed in close enough to where that appears to just be a straight line, then that means we can draw a line here and a vertical line there and create a right triangle. Where this point is our x1, y1. And this point is our x2, y2. We know that the distance of x for this side, if we wanted to find the length of this side, that would be our delta x. That's just equal to the absolute value of the distance between x2 and x1. That's all we're doing there. So to say x2 minus x1. Or you can say x1 minus x2, it'll still come out to be the same. That's why we put the absolute values up in there. Same thing with the distance of y. We wanted to find the length of that side. That's just y number 2 minus y number 1. Well, we can say that delta y is equal to the absolute value of y number 2 minus y number 1. Okay, so the length of just that one little straight line that we zoomed in to find is equal to the square root. Using the Pythagorean theorem, we could come up with that, or the Pythagorean theorem, the distance formula. We have the absolute value of x2 minus x1 squared. Well, since we're squaring it, we don't really need the absolute value because it's going to come out positive once we square it. x2 minus x1. Give that a little more room so it can look a little neater. There we go. Plus y2 minus y1 squared. Okay. So that works out fine and dandy for that one little line there. But now we have to do the same thing for this line, and 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 all the little itty bitty lines that we connected and made short enough to where they can create a circle or arc. So that curve, the entire curve between A and B, we'll call that S. Okay, and that's just equal to adding all of those straight lines up. So that's the sum from I equals 1 to n of the square root. So now we're not just talking about x2 minus x1, it's x3 minus x2, x4 minus x3. So we're just going to call that x of I minus x of I minus 1 squared. Plus y sub I minus y sub I minus 1 squared. Well, we can actually get that and change the notation a little bit. The sum from I equals 1 to n of the square root. Well, we know that x of I minus x of I minus 1, that's just our delta x. So we could say delta x squared plus delta y squared. Okay. Now, what if we multiply both of those terms by delta x squared over delta x squared? You could actually multiply by delta x squared divided by delta x squared. And that arc length would equal the sum from I equals 1 to n of the square root, and make the square root bracket a little bit bigger. So if we multiply the denominator by square root of x squared, then that'll just give us square root of delta x squared divided by the square root of delta x squared plus delta y divided by delta x squared. Let me separate those instead of putting them as one. Did the same thing over again. There we go. Okay, but we still have the numerator delta x squared, so we're just going to have that as delta x squared. So times delta x squared, get that a little bit of length. Here we go. Kind of separate that so it doesn't fall into the actual calculations. Okay, but we know with square roots, if you have two factors, you can get that square root and kind of break it up. So instead of having the factors underneath as your radicand, you can just break them up and have two separate ones. So that's the sum from I equals 1 to n of the square root delta x squared divided by delta x squared is actually just 1. So we can simplify that and just call that 1. Plus delta y squared divided by delta x squared. Since both are squared, we could just say that's delta y divided by delta x, and that entire quantity squared. Okay, and that will be multiplied by the square root of delta x squared. Okay, well, the square root of delta x squared is just delta x because the square and the square root cancel each other out. So we have the sum from I equals 1 to n, square root of 1 plus delta y divided by delta x squared delta x. So if you remember from Calc 1, you know that delta y divided by delta x, well, delta y, or your change in y, is just dy. And your delta x is just your dx. Oops, move that. Give a little more room. And since y is equal to f of x, we know the derivative of y is just the derivative of f of x, which is just f prime of x. So you know that arc length is equal to the sum from I equals 1 to n of the square root of 1 plus dy dx squared. And that delta x, we can just replace that with dx. So because we know we can get a more accurate arc length if the distance between the two are really, really, really close together. So that means that our delta x has to approach 0 for us to get an actual, not an actual, but a very accurate arc length. So that means that that arc length would have to equal the limit as n approach, well, not n approaches, as delta x approaches 0. Of the sum from I equals 1 to n of the square root of 1 plus, and you can leave it as dy dx if you want to, but I'll just say f prime of x squared dx. Okay, which is actually just the limit definition of an integral. So our arc length is equal to the integral from a to b, the square root of 1 plus f prime of x squared with respect to x. So this is your arc length formula. Yes.
Are we ever gonna have to like do the proof for that, or can we always just start using its formula?
You can always start using it. I only do that because depending on who you have for Calc 3 or real analysis or DiffEq, some of those classes do require proofs. So this is kind of like an introduction to how you would approach the proofs. But yeah, I wouldn't have you do any of that, at least not in this class. Okay. Anyone still writing? All right. Okay. So you have a general definition where you have one for, we have the curve with respect to x and one with respect to y. They're pretty much the same, but changing variables. So the actual definition, what if we let y equal f of x represent a smooth curve that is continuous. Let's say smooth continuous curve. That is differentiable on the interval from a to b. So for every value between a and b, the derivative exists. If you plug that value into your derivative, you'll get a defined number. So the arc length between A and B is what we just wrote. S is equal to the integral from A to B at the square root of 1 plus f prime of x squared with respect to x. Or instead of y is equal to f of x, what if we had x is equal to either f of y, or in this case, we'll just say g of y to avoid any confusion. So instead of the interval being between A and B, for the y-axis, we'll, like we always do, make it C and D. The arc length between, I'll say the values, y equals C and y equals D is the very same one, but we're going to switch it up. Instead of from A to B, it's going to be from C to D. And instead of the square root of 1 plus the derivative of f squared, it's going to be 1 plus the derivative of g with respect to y squared. Excuse me. All right, anyone still writing? Oh, okay. All right, you're welcome. Anyone else still writing? Oh, you're good? Okay. All right. Okay, so let's say, for example, we wanted to find the arc length of the graph of y is equal to x to the third power divided by 6 plus 1 over 2x on the interval from 1/2 to 2. So because you're looking for the arc length, the very first thing you want to do is find your derivative. So you want to find your f prime of x, or dy dx, whichever form of it you want to use. Okay, so we know that f of x, which is just your y is equal to f of x, is equal to 1 I can just rewrite that as 1 over 6 times x to the third power. And that 1 divided by 2 times x, I'll rewrite that as 1/2 times x to the negative 1 power. Okay, so your f prime of x is equal to 1 over 6 times the derivative of x to the third power. Should bring down the 3. It gives us 3x squared. Plus 1/2 times the derivative of x to the negative 1 power. We bring down the negative 1 and we subtract 1, so negative 1 minus 1 gives us negative 2. That means our f prime of x is equal to 1/2 x squared. 3 times 1 over 6 is 1/2. Minus 1/2 times x to the negative 2 power. If you wanted to, you could factor out a 1/2. You don't have to, but sometimes it helps. X squared minus x to the negative 2 power. Right, so once you find your f prime of x, now you're just going to plug it into the formula. So our arc length formula is just equal to the integral from a to b times the square root of 1 plus f prime of x squared with respect to x. And again, if you want to use dy dx there, that's perfectly okay. So that means our arc length is going to equal the integral from 1/2 to 2 of the square root of 1 plus your derivative f prime of x squared. So that's 1/2 times x squared minus x to the negative 2 power. And I'll use a bracket just to separate the parentheses. Don't want to have a bunch of parentheses in there. Squared with respect to x. Okay, well, 1/2 times x squared minus x to the second negative 2 power squared is just 1/2 squared times x squared minus x to the negative 2 power squared. So the integral from 1/2 to 2 with the square root of 1 plus 1/4 times x squared minus x to the negative 2 power squared with respect to x. Okay, we can kind of simplify this one, that term. Okay, so this term, we're going to go ahead and simplify that. We're going to put a little arrow there. So we have 1/4 times x squared minus x to the negative 2 power squared. Now that x to the negative 2 power, just so it's easier to work with, I'll just rewrite it as 1/x squared. But if you wanted to leave it as x to the negative 2 power, you can. So that's 1/4. And since it's squared, we're just going to go ahead and do that in this step. So x squared minus 1/x squared times x squared minus 1/x squared. Okay, so we have 1/4. And since we have two binomials, we can go ahead and just do the good old-fashioned FOIL method. Bring that down a little bit. There we go. So we have 1/4 times, we multiply the first terms, we get x to the 4th power. We multiply the outer terms, we have x squared times negative 1/x squared. This is just negative 1. Same thing with the inner term, x squared times negative 1/x squared is just negative 1. The last terms, you have negative 1/x squared times negative 1/x squared is just positive 1/x to the 4th. So we can combine these two terms, might as well get that out the way, and just give us negative 2. So if we distribute that 1/4, that gives us 1/4 times x to the 4th power minus 2 divided by 4. We just leave it as minus 2 divided by 4 just to give them all the common denominator. Plus 1/4. You can say 1/4x to the 4th power, but I'll just rewrite it as x to the power of negative 4, just to put it over here. We can always convert it back if we need it. Okay, so that means our arc length is equal to the integral from 1/2 to 2 of the square root of 1 plus, and instead of having 1/4 times this, we can just replace it with this right here. 1/4 x squared minus 2/4 plus 1/4 times x to the negative 4th power with respect to x. All right, so if we combine those constant terms, s is equal to the integral from 1/2 to 2. So we say 4/4 minus 2/4 is equal to 2/4. So you can have the square root of 1/4x squared plus 2/4 plus 1/4 times x to the negative 4th power. with respect to x. Yes.
For the 1/4,
Mhm.
first one underneath the square root sign,
Mhm.
how did it become x squared?
Oh, that should be x to the fourth. I think it was just me when I wrote it over here. I wrote it as x squared instead of x to the fourth. Thank you. There we go. So believe it or not, there's actually a reason we're going through all of this. It's a method to this lengthy process. Okay. So we can see here, we can factor out a 1/4 from each of those terms. Okay, so that's the square root of 1/4 times x to the fourth power plus 2 plus x to the negative fourth power. Or you can say 1 over x to the fourth. Doesn't really matter. We'll say 1 over x to the fourth. Now, this is where everything kind of falls into place. Because once again, whenever you have a square root and you have the square root of multiple factors, you can split them up. So it's 1/2 to 2 of the square root of 1/4 times the square root of x to the fourth power plus 2 plus 1 over x to the fourth. And over here, you can actually convert x to the fourth power plus 2 plus 1 over x to the fourth power you can convert that to x squared plus 1 over x squared squared. You can do that using the perfect square trinomials formula, but it's already long enough. I didn't want to go through all of that. So now this becomes, instead of timesing it by the square root of x to the fourth plus 2 plus 1 over x to the fourth, we can multiply it by the square root of x squared plus 1 over x squared squared. Because we couldn't do that up here because you had multiple terms. It had to just be one term. It could be multiple factors, but it couldn't be multiple terms. So you couldn't separate it here or here to do that. So we had to go through all of that to get it into this form. And we'll pick this up on the next page. Okay, anyone still writing? right. And let me just write down where we left off. Equal the integral from 1/2 to 2 square root of 1/4 times square root x squared plus 1 over x squared with respect to x. Oh, I got my dx here. Okay. Oh, luckily for us, the square and the square root cancel each other out. So know that arc length is equal to the integral, and the square root of 1/4, that's just 1/2. Square root of 1/4, that's just square root of 1 over square root of 2. I mean, not square root of 2, square root of 4, which is 1/2. So we can just replace that with 1/2 and bring it right out to the front. No point in writing extra steps just for that. Times the integral from 1/2 to 2 of x squared plus 1 over x squared. With respect to x. So from here, we can just go ahead and integrate each of those terms, finally. So the arc length is equal to 1/2. We have the integral of x squared, which is x to the third power over 3. And the integral of 1 over x squared, if you rewrite that as x to the negative 2 power, that's x to the power of negative 2 plus 1 divided by negative 2 plus 1, which is just 1 over x. And that's from x equals 1/2 to x equals 2. So once we get it in that form, we just apply the fundamental theorem, and we are that much closer to finishing. We go ahead and plug in our upper bound. So that's 2 to the third power divided by 3 plus 1 over 2 minus, go ahead and plug in our lower bound. And instead of having 1/2 to the third power over 3, I'm just going to factor out the 1/3 and say 1/3 times 1/2 to the third power. Oh, there we go. Plus, and that would be 1 over 2, so 1 over 1/2. So yeah, I'll just write it as 1 over 1/2. Okay, so our arc length is equal to 1/2 times 2 to the third power. 2 times 2 times 2 is 8. Plus 1/2. And 1/2 to the third power, 1/2 times 1/2 times 1/2 is 1 over 8. And 8 times 3 is 24, so that's 1 over 24. Distribute that negative, and that becomes minus 1 over 24. And And 1 divided by 1/2 is just 2. Because if you take 1 divided by 1/2, and you multiply it by 2/2, 1/2 times 2 is 1, so you end up with 2/1, which is just 2. So if we distribute that, it ends up being -2. Let me double check something. I think I saw a sign that should be just -2. Yep. So the integral of x to the power of -2 should be x to the power of -2 plus 1 over -2 plus 1. So that should be x to the -1 power over -1. So these should be subtraction. I knew it didn't quite look right. And there we go. So those 3 should be subtraction. So this should be subtraction. And if this is subtraction, that means this should be plus. There we go. Okay, so if we go ahead and simplify that. 1/2 times 8 divided by 3. So if you have a common denominator of 24, have to multiply this by 8/8. So we have 64/24 minus 12/24 minus 1/24 plus 48/24. Okay, so we have 52 minus 1 is 51. 51 plus 48 is 99. So that gives us x is equal to 1/2 times 99/48. No, 24. I'm jumping ahead. And that gives us 99/48. Which can be simplified if you divide both by 3. Or multiply by 1/3 over 1/3. And that gives you 33/16 as your final answer. All right, so any questions on that one? I know for a lot of these, you have to kind of work it around to get rid of that square root. So if possible, you always want to convert it to something squared so they can cancel out the square root. All right, anyone still writing? All right. So let's say, for example, if we wanted to find the arc length of the graph of y minus 1 to the third power equals x squared on the interval from 0 to 8. Excuse me. Okay, so we have x squared is equal to y minus 1 to the third power. Okay. Well, we can go ahead. It'll probably be easier to solve for x because we can just take the square root of both sides. It gives us x is equal to plus or minus the square root of y minus 1 to the third power. But we could also convert this a little bit more because we can rewrite this as y minus 1 to the third power and raise that to the 1/2 power to get rid of the square root. So we can always just say x is equal to plus or minus y minus 1 to the 3/2 power. Okay. So again, first thing I would do is just graph that just to get a visual. So if you did graph it, plug it into your graphing calculator or in Desmos, whichever one you decide to use. You would see if you plugged in x is equal to positive y minus 1 to the 3/2 power, it would look like this. And if you plugged in the negative, it would just go in the other direction. But we only need from 0 to 8, so there's no point in even bothering with the other direction. So we know here, when x is equal to 0, y is equal to 1. And the point where x is equal to 8, x have y is equal to 5. So we know the point 8, 5. Bless you. And we can get rid of this arrow on the end since we're not going on forever. We're just stopping at 8. Okay, so we're just looking for the arc length of that line segment. Well, not really a line segment, it's an arc segment. I think I just drew it a little bit with not enough arc on it. Yep, so it should look kind of like that. A little more arc on it. There we go. Okay, so we're just going to use the y minus 1 to the 3/2 power. Is used since the graph is positive from x equals 0 to x equals 8. we know here that, of course, y is equal to f of x. And that means x is equal to either f of y, but to avoid confusion, I'll just say we always just use g of y. We know that our arc length will equal the integral from c to d of the square root of 1 plus g prime of y squared with respect to y. That means our arc length equal the integral. And remember, for the x-axis, it's from 0 to 8. For the y-axis, it's from 1 to 5. Times the square root of 1 plus g prime of y squared. So that would be your g prime of y is your x. So that's y minus 1 to the 3/2 power squared. With respect to y. Be the derivative of y minus 1 to the 3/2 power squared. So write little dy dx. Or d dx or d dy. There we go. So we take the derivative of y minus 1 to the 3/2 power. That's the square root of 1 plus, and I'll solve that over here on the side. With respect to y of y minus 1 to the 3/2 power. From there, we can just use the chain rule. We bring down the 3/2 times y minus 1 to the 3/2 minus 1. So 3/2 minus 2 over 2 is 1/2. Times the derivative of y minus 1, which is just 1. So I'll actually write it out. So that's just 3 over 2 times y minus 1 to the 1/2 power times 1, but we're not going to worry about adding that over here. So that gives us 3 over 2 times y minus 1 to the 1/2 power squared with respect to y. So we know that square applies to both 3 divided by 2 and y minus 1 to the 1/2 power. So the integral from 1 to 5, the square root of 1 plus 3 divided by 2 squared is 3 divided by 2 times 3 divided by 2 is 9 divided by 4. and y minus 1 to the 1/2 power squared, the square and the 1/2 cancels out. So luckily, that makes it really simple because it's just y minus 1 with respect to y. So it doesn't look like we'll be able to turn this into anything squared to cancel out the square root, but it is still possible to solve it if we can turn it into something to where we can use the u substitution or another method. So it's not always, sometimes you can square it, but if you can't, you can kind of look at it and tell this is linear, so you wouldn't be able to do that. But you can convert it into something to where you can turn it to u to the 1/2 power du. Okay, so all we have to do now is get rid of this set of parentheses here by distributing that 9 divided by 4. So the integral from 1 to 5 times the square root of 1 plus, you have 9/4 times y, so 9/4y minus 9/4, so minus 9/4 with respect to y. Okay, so we can go ahead and combine our two constant terms. So we have the integral from 1 to 5 times the square root of 9/4 times y. And we have 5/5, not 5/5, 4/4 minus 9/4, which is negative 5/4 with respect to y. And we can go ahead and continue this on the next page. All right. Anyone still writing? Okay. All right. Oh, let me write down where we left off. Is equal to the integral from 1 to 5 square root of 9/4y minus 5/4 dy. Here we go. Okay. So both of those, just to kind of simplify it a little bit, we can factor out a 1/4. The integral from 1 to 5 times the square root of 1/4 times 9y minus 5 with respect to y. Okay, so just like before, you have two factors as your radicand, you can separate them. So integral from 1 to 5. So you got the square root of 1/4 times the square root of 9y minus 5 with respect to y. Okay, and just like before, we know that the square root of 1/4 is just 1/2. So we can get that 1/2 and just factor it right out to the front. So that 1/2 times the integral from 1 to 5 of the square root of 9y minus 5 of that one. You can just convert it to the 1/2 power. So we can make it 9y minus 5 to the 1/2 power. So again, we couldn't convert it into a perfect square trinomial because it was linear, but we can do the next best thing and convert it to a problem where we can use U substitution. Okay, so what if we let U equals 9y minus 5? That means we take the derivative of U and put it in differential form. Derivative of 9y is just 9. Derivative of negative 5 is 0, so that disappears. So it's 9 with respect to x. So if we divide both sides by 9, that means du divided by 9 is equal to dx. Shorten that line up a little bit. So we can convert this to 1/2 times the integral from 1 to 5. Instead of 9y minus 5 to the 1/2 power, you just make that u to the 1/2 power. I said dx. I'm so used to using dx, and it should have been dy. But same thing, just. Ooh, there we go. Okay. So we know that our dy, that's just equal to du over 9. Okay. So if we factor out that 1 over 9, just move that right out to the front. You know that's equal to 1/2 times 1 over 9. Times the integral from 1 to 5 of u to the 1/2 power du. So if we take those two factors and we combine them, that's just s is equal to 1 over 18. And the integral of u to the 1/2 power is just u to the 1/2 plus 1. So u to the 3/2 divided by 3/2. Give that a little bit of room so we can simplify that without an additional step. And we don't need the plus c because that's from y is equal to 1 to y is equal to 5. So we want to get rid of that fraction in the denominator, so we just multiply it by its reciprocal. So we multiply by 2 over 3 divided by 2 over 3. Where the denominator gives us 6 over 6, which is just 1, so those two cancel each other out. And this 2/3, we can get that and just factored right out to the front. That gives us 1 over 18 times 2/3 times u to the 3/2 power. Make that half a little bit neater. From y equals 1 to y equals 5. So again, if you wanted to, you can convert this to u of 1 and u of 5 values, but to me, it's just easier to replace the u. So if we simplify this, 2 goes into itself once, 2 goes into 18 9 times. That gives us 1 over 27. So it's 1 over 27. And instead of u to the 3/2 power, you can make that 9y minus 5 to the 3/2 power. This way we can plug in our y values, no problems. So now all we have to do is apply the fundamental theorem. And we are all set. We have 1 over 27 times, if we plug in y is equal to 5, we have 9 times 5 minus 5 to the 3/5 power minus 9 times 1 minus 5 to the 3/5 power. Okay, so that gives us 1 over 27 times 9 times 5 is 45. 45 minus 5 is 40. So that's 40 to the 3/5 power. Why did I put 3/2 power? Why did I put 3/5? Oh my goodness. I'm looking at the 5 there and just getting all mixed up. Should be 3/2 power, not 3/5 power. It should be 3/2. There we go. That's better. Minus 9 times 1 is 9. Minus 5 is 4 to the 3/2 power. And you could convert this by hand. I'm pretty sure they would. I think this is the only term that would simplify to something pretty straightforward. I think this would still, you can simplify it, but it wouldn't be anything pretty. But I'm pretty sure if they did have the answer, they would take this. But if they had something like this, they'd probably ask for a decimal approximation. So you just plug this into your calculator. So if you plug it into your calculator, you'd get approximately 9.0734. And it won't be exact, I'll say approximately. But yeah, if they wanted an exact answer, you just get the square root of 2 to the third power. So this would just be square root of 4 to the third power, which would just become 8. And this one would be square root of 40, which simplified, the only perfect square is 4 times 10. So that would be 2 square root of 10 to the third power. Like I said, it wouldn't be pretty. So, but this would be your exact answer. Again, I don't know how simplified you have to make that one for Newton to be happy. But if they ask for just the decimal approximation, I'd go as far as I'm comfortable with and then just plug it into your calculator. All right. Any questions on that one? All right. We should. Yeah, we should be able to get one more example out of here. All right. This way we'll be completely done with this section. Okay, so let's say if we wanted to find the arc length of the graph of y equals a natural log of cosine of x from x is equal to 0 to x is equal to pi over 4. So we know in this case, our f of x is equal to the natural log of cosine of x. Okay, so if you remember from Calc 1, the derivative of a natural log of some function of x is equal to the derivative of that function divided by that function. That means for this one, we wanted to find the derivative. In this case, your g of x is cosine of x. So the derivative of the natural log of cosine of x is, let me give that a little more room, it's a little bit close. It's equal to the derivative of cosine of x divided by cosine of x. And we know the derivative of cosine of x is just negative sine of x. So that's just going to be negative sine over cosine. Move that over negative sine of x over cosine of x. Well, that negative sine over cosine, we can rewrite that as just negative tangent. So that means our arc length, which is equal to the integral from a to b of the square root of 1 plus f prime of x squared with respect to x. We plug in everything that we know. That means your arc length is equal to the integral from 0 to pi over 4 of the square root of 1 plus f prime of x squared. So that'll be negative tangent of x squared. Oops, we got my squared. There we go. With respect to x. So we can rewrite that as the square root of 1 plus negative tangent squared is just tangent squared, since negative times negative is positive. So it's tangent squared with respect to x. Now, this is one situation where we can get rid of the square root. Because if you remember, we know that sine squared plus cosine squared is equal to 1. Okay, so if we divide each one of those by cosine squared, move that a little further down, we have tangent squared plus 1 equals 1 over cosine, which is secant squared. Oops, there we go. So that 1 plus tangent squared, we can replace that with secant squared. So 0 to pi over 4 of the square root of secant squared of x with respect to x. Here, the square root cancel each other out, so we're left with just the integral of secant. 0 to pi over 4 of secant of x with respect to x. And we know the integral of secant is the natural log of secant plus tangent. Okay, so we have the natural log of the absolute value of secant of x plus tangent of x. And that's from x equals 0 to pi over 4. Oh, forgot my integral sign. Oh, no, I didn't. Okay, now we apply the fundamental theorem. Go ahead and plug in our upper bound. So that gives us the natural log of the absolute value of secant pi over 4 plus tangent pi over 4 minus, let's go ahead and plug in our lower bound, the natural log of secant of 0 plus tangent of 0. Okay, so if we simplify this, we know this has natural log of secant of pi over 4, which is square root of 2, plus tangent of pi over 4, which is just 1, minus the natural log of secant of 0, which is 1, plus tangent of 0, which is 0. Okay. Well, we know the natural log of 1 is equal to 0. Make a little side note of that. Natural log of 1 is equal to 0. Make that a little clearer. So that just disappears. So that leaves us with our arc length is equal to the natural log of the square root of 2 plus 1. Okay. But if they want the decimal approximation, you plug that into your calculator, you should get 0.8814, depending on how many decimal places they want it rounded to. All right, any questions on that one? All right, so we'll go ahead and stop there because I don't think there are any examples we'll finish in under 10 minutes. All right, now we'll see you tomorrow. Hi.
I have a question.
Sure.
For this assignment, when did you want that by? And like, what is it?
Well, the lockdown browser quiz, that is just,
That's just a quiz for what we've been learning.
nope, that is just to help you prepare for the exam. Have a good day. All right, you too.
Oh,
Yep, that's just so you can have your lockdown browser. If you're going to use your computer, you can
just to get it ready?
Yep, you can already
Oh,
have
okay,
it on
I
there.
got you. I was
So this way,
confused
yeah.
because it was like 100 points. I was like, I
I
don't
don't know,
know.
it shouldn't be 100 points. I don't know why I said
Yeah, I
that.
know, I was confused.
Yep, it's like a really easy question just to
Yeah.
help you get it ready for the quiz. So this way, a lot of people would just wait till like the day of the quiz
Yeah.
and try to do it,
Yeah.
and then it sometimes doesn't work.
And then the final is in person, but I read somewhere like you need 60% minimum to pass. or something
That's
like
only for online classes.
Oh,
so
okay.
if this would have been like 100% online class,
that. Then
then,
okay.
then you
yeah.
need 60%.
And you said we could use like a graphing calculator. On
Yeah,
it, and
yeah.
like we can bring it's like open note or like you bring note card. Something
You
like
can
that.
bring a note card, but
Okay.
I'm trying to see. Normally they have like a 3x5 note card for,
Yeah. So you can bring like
For
a
Calc
note card.
1.
Yeah.
but Calc 1 is departmental final,
Mm-hmm.
and Calc 2 I'm making up the final, so I
Oh,
don't
you're
have to
making
follow departmental rules.
Yeah. Okay.
So that's the only
Okay.
one good thing about it.
Oh, I got you. Yeah.
So-
So like that's why you can use the calculator.
Yep,
on it.
exactly.
I got you.
So-
Thank you so much.
Oh, you're welcome.
Hi.
Hello.
I sent you a message on Canvas,
Mhm.
but yesterday I tried to log into the class online,
Mhm.
and when I click the button, like it says like the new conferences and past conferences, but
Mhm.
there's nothing there.
Okay. Yep, I was on there last night because a couple of people had issues with that.
Okay.
So what I did, let me put the PC on the screen. You go to, let me go to the homepage. So here he is. So the first two lectures, I put the links to them.
Okay.
So they're already there. They still might only hang there for like maybe 5 days. So
Yeah.
from the 18th, it might disappear on the 23rd or 24th.
Okay. Sounds
So
good.
the only thing is, like I said, when I download this, we only get like 500 megabytes of memory.
Yeah.
So literally, I downloaded one video, it filled up the memory.
Okay.
So it was one of those
Okay,
things. Where
gotcha.
that's why I had to put the link there. So if you click on the link, it'll take you right to the video. But
Okay.
it should have sent it automatically. That's where I was online with them yesterday trying to
Okay.
figure out what was going on. But
Okay, perfect.
because it didn't see you there automatically, it's like, okay, you have to create a link and hopefully it works. But if it doesn't work, they'll still have it. So I'm like, I won't know if it works today until everybody gets online, and
Okay.
hopefully I don't get any emails saying we still can't see it. So
Okay.
all
Well,
right,
thank you.
you're welcome.
Have a good day.
You too. All right, let me, yeah, here we go. All right, thank you, Alyssa. You have a good day too. All right.